Hello everyone, my name is Luke Mickey and welcome to my channel. Today we're going to talk about subspaces, and we're going to define what a subspace is. We're going to show the subspace criteria, i.e. how we show something is a subspace or prove it's not a subspace. And we're going to go through several examples of this. So this is the sort of thing that you will do in most linear algebra courses, most likely in your first ever linear algebra course. So firstly, we're going to go over this theorem. And this theorem tells us what a subspace is and the criteria of it for which it must fulfill. So the theorem is, let V be a vector space. So common examples of vector spaces are R2, R3, complex numbers, for example, the real numbers, things like that, over a field F. So the field is where we take our scalars from. So for example, that could be the real numbers, it could be the complex numbers, it could be the rational numbers, or it could be integers or natural numbers even. But most likely we're going to be looking over, for example, RC usually. And we let W be a subset of V. So not the full, it might not be the full set of V, might not be all the vectors in V, but it's just a portion of them. It could just be a portion of them. It could be all of them, but that's just a useless statement really. You really want just to have a selection of vectors from the set V, because if you have all of them, you're just in the space V anyway. So we let W be a subset of V, which is non-empty. Okay, so right now we have the definition of a subspace. So the subspace is a non-empty subset of V. So that's our first bit. Now, for W, to be a subspace, we require if V and W are in the subspace W, or in the subset W, then V plus W must also be in here. I.e., if we add two vectors in the subset, then we must still stay in that subset once we've added them. So adding two vectors must allow us to stay in the same space W. If we leave the space by adding two vectors from the set, then we're not closed under addition, and that means we won't be in a subspace. Also, if V is in W and alpha is any scalar from the field F, then if we take our vector V and we multiply it by alpha, we must also stay in W. So multiplying a vector by some value, some number, for example, it must stay in the subset W of V. If it leaves W, then and it's not a member of W, then we are not closed under scalar multiplication, and hence we're not in, where we don't have a subspace. So this is what we call closure under addition, and this is what we call closure under scalar multiplication. So we're going to go through a few examples on how you show that something is a subspace or it's not. So for showing something is a subspace, we need to prove three things. We need to show that it's non-empty from the theorem, and we also need to show that it's closed under addition and it's closed under scalar multiplication. To show something's not a subspace, it's easy just to show that one of these things isn't satisfied. Most of the time, it's going to be something like there's no zero vector in it, because if we're closed under scalar multiplication, then it means that if we take the zero scalar, well, just zero, and we multiply it by the vector, we're always going to get the zero vector. And so if the zero vector is not in our subspace, then well, not in our subset, sorry, it can't be closed under scalar multiplication, and hence it's not a subspace. So that's things that we only use to show that it's disproved that it's not a subspace. Anyway, so our first example. So we'll go to our first example. So let me just start a new page here. First example, we're going to let the vector space V be R cubed, and we're going to consider the following non-empty subset W equaling the set of all vectors of the form A, 0, 4A, where A is a real number. So first we need to show, is this set W non-empty? So it is non-empty because we could take A, since A can be any real number, we could take A, for example, to be equal to 0. And in that case, we'd have the 0, 0, 0, the 0 vector is in W. So W is not equal to the empty set. It is not empty. So first one, tick. Second criteria, closed under addition. So in this case, we need to take two vectors from W. So we'll let U be in W. We'll say let U equal A, 0, 4A. And we'll say that's in W. And we'll let V be equal to, instead of A, we'll just use B. But B will still be a real number. So it's still the same form for B. And this will be also in W. And we will add them together. And if we add them and we stay in, and we get a vector of the same form as this, then we're good. We're closed under addition because we're staying in the space when we add the two vectors together. So U plus V is equal to A, 0, 4A plus B, 0, 4B. And this is equal to A plus B, 0, and 4A plus 4B. And then we could take the 4 out and say A plus B, 0, 4 lots of A plus B. Now, A is a scalar, B is a scalar, so A plus B is a scalar, A plus B is a scalar, right? So in this case, this vector here is of the form of what we have in W. So it is in W because it's of the same form as this. So we are closed under addition. Now we'll do closure under scalar multiplication. So we'll take alpha to be a real number. We'll take alpha to be a real number, and then alpha of U will be equal to alpha lots of A, 0, 4A, which is then equal to alpha A, 0, 4 alpha A. And again, alpha times A is a scalar. So because alpha times A is a scalar, then this vector here has exactly the same form as the vectors in W. So we are staying in W. So by multiplying our vector by a scalar, we're still in the space, we're still in the subset. So this is also W. So we've checked all criteria and we have satisfied all criteria. So therefore, W is a subspace of V. Little wee box, sorted. So that's our first. So that was a subspace. Second example we'll do is we will again consider our R3 as our vector space. And we'll consider W to be equal to A, B, 1, all vectors of the form A, B, 1, where A and B are real numbers. So let's first check that it's non-empty. So it's non-empty because we take A to equal 0, B to equal 0, for example, and we'd end up getting a vector of 0, 0, 1, which would be in W. So W is not the empty set. It's definitely non-empty. Now, because we've got this 1 here, I have a feeling we're going to fail over scalar multiplication, because if I take the zero scalar and I multiply it with the vector, just any vector in that space, I'm going to get the zero vector. And the zero vector is actually not in W, because all those vectors have to have a 1 in where you'd have the z component. The z component would be 1, right? So I'm going to use that. So take alpha to be equal to 0. Then alpha of, and then let u be equal to just AB1. Then alpha u equals 0 lots of AB1, which is 0. But 0, 0, 0 is not in W, because you'd have to have a 1 here, and it's a 0. So because the zero vector is not in W, and for example, and 0 is a scalar, then we are not closed under scalar multiplication. So in that case, this is not a subspace of V, because we've failed under closure of scalar multiplication. And you'll find that's a very easy trick. Well, not a trick, but it's a very easy method of showing that it's not a subspace, is checking that the zero vector is present. If it's not present, it cannot be a subspace. Okay, another question. Let's take again V equaling R cubed, and we'll have W be the set of vectors x, y, z, such that x plus y plus z is less than or equal to 0 for all x, y, z in real numbers. So again, we need to check if it's not empty. So it's not empty, as if we take x equals 0, y equals 0, and z equals 0, we'll get the fact that the zero vector is in W. And why is the zero vector in W? Well, it also satisfies this x plus y plus z, right? Because if x is equal to 0, y equals 0, z equals 0, then 0 plus 0 plus 0 is equal to 0, and this is less than, or actually equal. Well, in this case, it's equal to 0. So this equation here is satisfied. So the zero vector is in W. So W is not the empty set. So far, so good. Now, let's try scalar multiplication again. So if we take, well, because of this criteria here that x plus y plus z has got to be less than 0, then we're thinking that if we take a scalar, like a negative scalar, for example, say take -1, then maybe this criteria will fail. Maybe negative x plus negative y plus negative z will not be less than or equal to 0. So let's just see if we can check that. So let's take alpha. So let's take u to be equal to x, y, z, which is in W, and alpha to be equal to -1. Then alpha of u is equal to negative lots of x, y, z. That's negative x, negative y, and negative z. Now, is this in W? Well, let's check. If I check negative x plus negative y plus negative z, that's going to be the same as if I take a negative out as a common factor, I'll have negative x plus y plus z. Now, x plus y plus z has to be less than or equal to 0, because the vector u is in W, so x plus y plus z is less than 0. So this thing here is less than or equal to 0. But then, so it's a negative number. So because it's a negative, because this thing here is a negative number or 0, then a negative times a negative is positive. So this thing is either greater than or equal to 0, which means that this vector is not necessarily in W. So this vector is not in W necessarily. It's only in W if alpha, if x, y, and z is 0. That's it. So in that case, no, W is not a subspace, as we are not closed under scalar multiplication. Because remember that we can take any scalar here. It's not just, I've just used -1 to show that it doesn't work. And if it doesn't work for alpha equals -1, then it's disproved. It's a counterexample, and it shows that it's not an actual subspace. Right. Next one. Next one we're going to try, and we're going to use polynomial. So we'll have V equals P2. So P2 is the space of all polynomials of degree at least 2. Right? So if I write that out, we're going to have W. We're going to have, those are going to be polynomials of the form ax squared plus bx. Such a, b are real numbers. So this is the following subset of V that we're considering here. So let's check if it's not empty. So if we take A equaling B equals 0, then 0x squared plus 0x equals 0. So it's a 0 vector for this space. And it's of that form ax squared plus bx, because we've set A and B to equal 0. So the 0 polynomial is in W. So W is non-empty. So number 1, tick. Next one, let's consider addition closure. So we'll take 2 polynomials in W. So let U in W, we'll let U equal ax squared plus bx, and V equal cx squared plus dx. And both of these are going to be in W. Then we will add them and check that the result is still in W. So U plus V is equal to ax squared plus bx plus cx squared plus dx. And we can factorize this by collecting common terms. So we'll get a plus c x squared plus b plus d x. And as you can see, that this is a scalar, this is a scalar, so it's in the same form as everything in W. So this thing here is indeed in W. So we are closed under addition. Now, scalar multiplication closure. Yes, and multiplication. I apologize for my handwriting. We'll take alpha to just be a real number. Then we will have alpha u to be equal to alpha lots of u, which is ax squared plus bx, which is alpha a x squared plus alpha b x. And because alpha is a scalar, scale times a scale is a scalar, so alpha a and alpha b scales. So this is in the same form as everything in W, so this is indeed in W. So yes, W is a subspace. Finally, the last example is perhaps one of the sneakier ones. And it's a bit strange because it's matrices and not polynomial vectors. So we're going to consider the space of all n by n real matrices. So n by n over field R. I'm going to say that W is the set of all invertible matrices. Now, this one's quite sneaky because it's quite difficult to, you can see that W is non-empty because you could consider like the identity, for example, which is invertible. But then trying to do closure under addition and scale multiplication might be difficult, because you are then having to consider you're considering just n. You're not considering an actual number. You're considering infinite amounts of matrices, infinite dimensions, if you have to do for every case of n. So it's quite difficult to do that. So you're probably thinking, well, it's probably not a subspace, and you'd be very correct in saying that. And if you hark back to what I said before, that the zero element, well, zero vector must always be in subspace. So we can see here that zero vector must be in W for it to be a subspace. This follows by scalar multiplication. Closure. Now, is the zero vector in W? Well, if I consider just, say, the 3×3 zero vector, no, zero matrix, sorry, then is this invertible? Well, for a matrix to be invertible, the determinant of this matrix, let's call this M, must be non-zero for M to be invertible. But this matrix has a zero determinant because we have a zero row. We have at least one zero row. We actually have three, so the determinant of this matrix is 0. So this means that M, because M, the determinant of M is equal to 0, M is not invertible. And hence, the zero matrix, which I'll just write as a zero vector here, is not in W. And hence, W cannot be a subspace, because every subspace must contain the zero vector, because it's a consequence of scalar multiplication. Okay, guys, I hope you enjoyed my video. I hope it wasn't too long. I know I went through quite a lot of examples on that, but I hope it helps you with your studies. Anyway, till next time, goodbye.